This is IAQ Radio, Indoor Air Quality Radio, the voice of the indoor air quality industry, with your hosts, Radio Joe Hughes and the Z-Man, Cliff Zlotnick. And now, Radio Joe Hughes.
Good day and welcome to IAQ Radio Plus, episode 651. We've got a great show today. We've got Dr. Kishor Khankari. We're welcoming him back, and we're going to spend the day talking about computational fluid dynamics, a topic we haven't really hit very hard, so I think I'm looking forward to that. We're going to talk about it and compare how we use it to help with indoor environmental quality issues. So before we get started, let's thank our sponsors. They're the reason we can continue doing the show. Our marquee sponsor is Instascope at instascope.co. Our association sponsors are the American Industrial Hygiene Association, AIHA.org, the American Conference of Governmental Industrial Hygienists, ACGIH.org, the Cleaning Industry Research Institute, CIRI Science.org, the Indoor Air Quality Association, IAQA.org, the Restoration Industry Association, restorationindustry.org, the Institute for Inspection, Cleaning, and Restoration Certification, IICRC.org, Healthy Buildings America 2021, HB 2021-America.org. Industry sponsors are AEML Laboratories, AEMLINC.com, Particles Plus, particlesplus.com, Gray Wolf Sensing Solutions, graywolfsensing.com, TSI Inc., TSI.com, Sunbelt Rentals, sunbeltrentals.com, April Air, April, AIRE.com, Healthy Indoors Magazine, healthyindoors.com.
And now you can win a cool prize. It's time for the IAQ Radio Trivia question. Be the first to correctly answer. Simply email your answer to czlotnick@cs.com. Or if listening live, just text your answer from your computer. And now, here's the Z-Man.
Hello, everyone. Happy to report that John Lapotier was first to identify January 7th, 2022 as the holiday of Orthodox Christmas. The IQ Radio Trivia question for today, January 14, 2022, has been sponsored by TSI Inc., an industry leader in the precision instrumentation for the monitoring of indoor air. Learn how to expand your IAQ investigations at tsi.com. Here's today's IAQ Radio Trivia question. Name the scientific subdiscipline that studies the motion of air. Back to you, Joe.
All right, thank you, Cliff. We've got today Dr. Kishor Khankari. He is the founder of AnSight LLC, and he is a specialist in computational fluid dynamics with a Ph.D. in the topic from the University of Minnesota. He's also an ASHRAE Fellow and Distinguished Lecturer and currently serves on the ASHRAE Board of Directors. Welcome back, Dr. Khankari.
Thank you, Joe. Thank you, Cliff. Thanks for having me. First of all, I should thank all of you, Joe, Cliff, and John, for doing this for such a long time. And I understand this is a 651 show. It's a lot of efforts you put it in, and this is good for our industry, good for indoor air quality, and you have all our support for doing this. Thank you.
Thank you.
Thank you. We appreciate that. Hey, by the way, I want to mention, I forgot to mention that Healthy Buildings America starts Tuesday next week, folks. So you're not too late, and it's all virtual. You can jump online and check it out. So if you get a chance, check it out. Anyway, let's get into this whole computational fluid dynamics. It sounds exotic, and I guess it is a little bit exotic. Can you explain to listeners, what is CFD and how does it work?
Yeah. Good. Thanks for asking me that. And it is exotic for some reason. Some people think CFD stands for colorful dynamics, and sometimes they spell fool as fool, FOOL, because those pictures can fool you. Well, it's not really that colorful dynamics. It's a computational fluid dynamics. It is a science. And what that science does is it simulates processes like fluid flow, flow of water, flow of air, flow of slurry, or whatever that fits the definition of fluid in fluid mechanics. It simulates heat transfer, mass transfer, moisture migration, chemical reactions, and so forth. So this is a science based on the laws of physics. So it's not a statistical model. Like people collect the data and they fit the curve on that data. So that curve fitting and that equation is as good as it relates to that data. If somebody collects data for Detroit and comes up with some conclusion, like in statistical model, well, it can talk about the people around and in Detroit, but if you take it to New Delhi or London or somewhere, that may not be valid. That's not true with CFD. CFD is based on the physics of air motion, in our case, in HVAC industry, physics of heat transfer, physics of mass transfer. And so those laws are universal. So if we find something that's happening in the Detroit building, it may be just true in London and New Delhi and anywhere else in the world. So far, you don't build the buildings on the moon or Mars. So then we will talk about those laws sometime later. But so far, we are on the Earth. Those laws work. And what are those laws? Those are like we all learned in our engineering, probably the conservation of mass, conservation of momentum, conservation of energy. Those are the basic laws. What happened is from centuries, people have developed what they call the differential equations. They describe the air motion, transport of heat, transport of particles, transport of gases, and they are very good, solid basis for that. The problem with those equations is you cannot just solve like algebraic equation and come up with a formula that you can stick on your computer or on your calculator and say, well, if I'm sitting here, how am I going to feel? Am I going to feel too hot or too cold? Or what am I breathing here? What's the indoor air quality? I can't do that. Those equations we cannot solve by what we call analytical methods. So what happens is they went back to the drawing board and said, well, how did we come up with those equations? And then they take that and basically divide, suppose it is in your room, Joe, we want to know how air is moving. We will divide your room on the computer into small pieces and then solve that each equation iteratively. It's like churning the thing, and come up with the solution, which is a three-dimensional solution. So what CFD gives you is not just the value at one point, but the entire room in three dimensions at millions and millions of points, how the temperature looks like, how the velocity looks like, airspeed, how the concentration of particles or gases look like. And that gives us the insight into what is going on in the room. So I hope I explained it.
I think it's going to help to put some graphics up and show folks a little bit more. Like, you've used CFD to help improve indoor environmental quality. Can you give us a little case study maybe?
Yeah, I will. But before that, I want to explain that why we need this. I mean, for example, see, air is the main carrier of heat, moisture, contaminants in our business, correct? Those we are involved in HVAC business, air is our primary fluid, primary carrier of heat. And air determines how we feel, airspeed, temperature around us, the contaminants in the air, they determine our indoor air quality. The problem is we cannot see how air moves. I mean, nobody can put the goggles on and say, oh, Now I know, I see how the air is going. Those goggles are not there. Those vision to see the air movement are not there. And even if somebody invents that, to how to see the air motion, it is too late. Your building is already built, you are living there. What if you feel too cold every day there? What are you going to do? If you can see that before you build the building, while your design is on the paper, that will make a lot of sense, because then you will see where the problem is, why people are feeling cold in this building, why there is a hot spot here, or why there is not enough good air in this spot. If we can find out and do the cause and effect analysis and put our microscope on that room, on that space, we will be able to refine our design and make it better. It's a proper due diligence. And that's why we need tools like computational fluid dynamics to help our design go in right direction. Okay. So let me share my screen and I will show you some examples here. And
I think you also, when we talked earlier, you kind of used the analogy of a glass of water.
Yeah.
If the glass of water is dirty, or like sometimes I get some brown water here because of iron in our local water, and it's got to be filtered out, you can see that. So what you're trying to do is help us visualize what's going on in the air.
Exactly. And that's the purpose of this three-dimensional computational fluid dynamics simulation. I want to emphasize one more time, this is a science. This is based on the physics of the air motion. This is not something, an artistic rendering of the arrows, how air will move. It is not my intuition. It is the physics of the space telling me. So I'm going to walk you through several examples here very quickly. So
before you do, let me ask one more question, Kishor.
Yeah.
Why was this initially developed?
Oh, that's a great question. It was developed from aerospace industry to start with. Remember, when you put people 30,000 feet in the air, you cannot take the risk of, oops, I forgot to convert the unit on my calculation. You can't. So to advance the science of aerospace, that's where its origin is. And about 6, 7, 8 decades ago, people started doing this. At that time, the computers were not as powerful as they are today. And the science was not very well developed. But these professors and scientists, they worked hard to use this science to understand the lift and drag on airplanes, correct? On the airplane wings, and so forth. And over the years, what happened, the computational power on the computers has increased tremendously. You can do these simulations on your laptop today. That's the case. At the same time, the science of this numerical science of computations has advanced a lot. And there are commercial software they can be used to do this thing. So now CFD is not just limited in the hands of professors or very few experts, or not just in the universities. This has been used almost for everyday application. Just to give you an example, this Dyson vacuum cleaner, which is one of the probably the best vacuum cleaners as advertised. This person in England developed this vacuum cleaner using computational fluid dynamics. So the whole concept, he put it on the paper and created a CFD simulation out of it. And then he kind of optimized each and every aspect of this and made sure that it works on the computer very well before he built his first prototype. So automobile industry, all the car companies are using this. How many miles you get per gallon, that is related to the drag on your car. And so previously, a couple decades ago, they used to make this mock model and take it to the wind tunnel to determine the lift and drag on the car. And then they will come back and then they will smooth the front windshield part or the side mirrors and go back and put it in wind tunnel again. Now there is a virtual wind tunnel. They use computational fluid dynamics just to optimize the aerodynamic shape of the car and they can actually know what miles per gallon it will do. You get a hiss on the car, the wind noise. They can hear that wind noise just from simulation, not from actual car. And then they can buff the shape of the side view mirrors and minimize that noise. The car inside environment, nowadays cars are very sophisticated. You need all the best indoor air quality and comfort in the car. This is all done on the computer to optimize this thing.
I didn't think of that. Sound is like a fluid as well, I guess, huh?
Yeah, I mean, the wind noise is created by the fluctuations of air on the surface, and that turbulence creates that vibration that creates the noise. So if you can simulate the airflow around the car, around the side view mirrors accurately, you can convert that pressure fluctuation into the noise, into the sound, and you can hear it putting the earphone on the simulation. The critical thing, like people, the heart valves, correct? You can't experiment or any medical device. It has to be done using simulations to develop that. The best example is the failure of nuclear reactor. How are you going to experiment it? Are you going to kind of fail the nuclear reactor? It's too dangerous to do that. Simulations help us to understand that. I will give you a simple example where we need CFD. We all design atrium for smoke exhaust, correct? And we want to make sure when there is a fire in the atrium, the smoke exhaust system will work properly. Now, what's the commissioning on this one? We move with the small smoke bombs, this fire marshal bomb, and say, oh, okay, smoke is good. That's not enough. I mean, when the fire occurs, either one of the sofa or furniture or something catches the fire and there is a huge source of fuel there, and that whole plume is going to rise. So we don't take the junkyard sofa and put it on the fire in the atrium just to make sure my smoke exhaust works. We don't do that. In such cases, the only way we can test it is through simulation. So, okay, let me go back to some examples here I have. And so this is the tale of two office spaces. And this is published in ASHRAE journal. These are two identical office spaces. There are 6 people sitting here, separated by a cubicle wall, correct? And there is one person who is infected, let's say with flu or COVID or whatever. And in one case, you have one 4-way diffuser where the air comes into. And then this red square is where the air goes out from the space. Simple thing, correct? In another example, it's the same office space, but instead of bringing air just from one diffuser, I divide it among the 2 diffusers here, 2 blue squares. I'm not increasing the amount of air. I'm just distributing it in 2 places. And instead of taking it out just from one red square, the return, I created one more grill here, 2 grills, 2 supply. And you will see it makes a tremendous difference. These lines show how the air is moving into the space. In one case, air moves all the way to the other end and then moves and circulates. Here, the air comes from 2 diffusers and they create their own tiny recirculation patterns. Here, I call it aerodynamic containment, and I will explain it to you why. So what
Aerodynamic, say aerodynamic what?
Aerodynamic containment, and I will explain it to you why I call that arrangement as aerodynamic. Now, this animation is self-explanatory. What is happening? This guy is coughing, sneezing in this cubicle, and when you have only one supply and one place to take the air out, all the germs go into other cubicles, infect other people, and get out of the room. If I create the path of least resistance for those germs to leave the space, instead of staying there for a long time and circulating, you can see those germs, they come out and they go, hey, here is my exit. Like if you're driving on highway, your exit comes, you don't go 10 miles further and take U-turn and come back. You take the path of least resistance. You take the first exit. Germs are doing the same thing. They are finding, hey, here is my exit. I don't need to go to another cubicle. I can get out from here. Okay. Now, this is computational fluid dynamics simulation. What it is telling me, two grills, two supply diffusers are better than one, and two return grills are better than one. That's what it is giving you the direction. It is not exactly when people will sit, oh, exactly the germs will follow that path. There is a possibility that second arrangement, this arrangement is better than the first one. So if you take this and color it by the, what is the probability that people will get infected in this space, okay? So this is the kind of cut plane at your nose level. This is another thing to understand. What happens at your breathing zone? I call it breathing zone. It is about 4 to 6 feet height from the finished floor. That is important. What happens near the floor and what happens near the ceiling is not as important as what you breathe in and what you breathe out. So if I look at the breathing plane of the people at about 4 feet height from the floor, what it tells me, I have very high probability of infection with this kind of ventilation arrangement. More people will get infected, even if they are 6 feet apart. See, we are talking so much about this social distancing. Social distancing is as good as your airflow around you. If you have a bad airflow pattern, as in this case, 6 feet distance doesn't work. You will still get the germs, and there is a high probability of getting infection. Just put two supply here, divide that air at two places, and bring it down and take it out from two places. What you are doing, instead of supplying the air at one place and let it move, you are supplying at two places for the people. And so this green color turns to blue, means I reduce the probability of infection substantially, simply supplying the flow of air over the people. Let me explain it to you further. Think about this cloud you are seeing. This cloud is where the infection probability is 10% or higher. Those who are under this cloud, there is a 10% chance or more to get infected. And how much is that cloud? It is occupying almost 50% of the entire room. It's pretty high. All the people, all those 6 guys are all immersed in that cloud of high probability infection. If I improve my ventilation here, bring air in a distributed fashion and take it out in a distributed way, I reduce that cloud size to 36% from 50%. I'm not doing anything else. I'm not increasing airflow. I'm not using any air cleaner. I'm not using any UVC. Just I'm using the good clean air to dilute and mitigate the probability of infection of the contaminants here.
That's interesting. Now, you could also, if you wanted to, take that room divider out and look at it again and see with and without the room divider how again those germs or virus would spread. And
yes, that is another good point. With the simulations, we can move the people around. We can make another person infected. I can increase or decrease the height of partition. I can take the partition out. I can make this room as a classroom and study the same thing without having a physical facility to do these experiments. I can use physics to understand this, to gain the insight, to learn the lessons from here. And by the way, my conclusion from this study is those barriers are not doing anything here. They are kind of not too high barrier here. So there are studies, people are showing, people are putting those plexi glasses in front of the students.
yes,
They are in fact creating more turbulence in the room than helping it. Remember, the spread of COVID, for example, is prominently by the airborne pathogens which ride the air. The droplets, it can catch the droplets. Somebody sneezes or coughs, and if they eject the large droplet, the plexiglass can catch them. But if they are airborne and moving with the air, glass is not going to hold it, correct? It's going to go anywhere the air flows. Does that make sense?
absolutely. Now, there's a question here. I'm not sure if you're able to see that, but
No.
CFD has been an important part of COVID response in helping us understand exposure in relation to different ventilation scenarios. A missing component has been the lack of attention to epidemiology, which could be used to see the actual transmission between COVID occupants under different setups. Is anyone working on this?
Yeah, I mean, several people are working on this, and this is a very good comment because this should be a multidisciplinary approach. CFD specialists, HVAC experts, epidemiologists, doctors, all should work together. Because what I'm doing here, I'm looking only at the airflow, correct? How air is moving. And if there is a small germ particle as a result of this airflow patterns, where the germs will go. But I need epidemiologists to tell me if the load, viral load is this much, and if that much load comes to me, what is the probability of me getting infected because of that? And then we need a doctor to tell me that if these things are inhaled by us, then what is the probability of getting sick out of this? Whether it will just stay in my throat or in my nose, or whether it will go in lungs, and how long it will take me to get sick or get cured from this thing. So people are doing these studies, and because of the pandemic, this awareness has gone up. What I'm concerned about is people are still not understanding that the room is not a well-mixed room. So many years, the HVAC engineers think room is like a coffee cup, and I put a creamer in my coffee and stir it, I get a nice one homogeneous fluid. If you put a germ in a room, it doesn't get instantly mixed like your creamer in a coffee cup. It moves. There is a high concentration and low concentration. And we need to understand that what makes it high concentration and what causes low concentration. What I need to do to reduce that concentration level, not in the entire room, but at my breathing zone. Because I breathe out and breathe in at 4 to 6 feet height air volume. So people stick the sensor in their return duct or exhaust duct, and they say, oh, I have very good indoor air quality in this room. And I question them, how do you know? How do you know? Your sensor is in the exhaust duct. not at 4 to 6 feet height from here. What we need to monitor and understand and appreciate that airflow movement, airflow patterns play a very important role in our indoor air quality. And we should be monitoring at the breathing zone, not near the ceiling, not in the exhaust duct, not near the floor. We are not evaluating the vacuum cleaner. We are trying to understand what am I breathing in.
Cliff, do you have a follow-up?
Yeah, I do. Kishor, I've got a question for you.
Yeah.
Why can't you use either theatrical smoke or water vapor droplets produced by ultrasonics to help assist being able to see these air patterns?
Very, very good question. And people are still using it. They were using it for many decades. The thing is, you need to have a room, Cliff, to inject the smoke. I mean, you need to go to either an office space or a classroom or somewhere, and everywhere you go, you need that smoke, theatrical smoke or water vapor, water you are talking. We need to go and do it. And if you do that, how many times you will do it? How much you can see through it? And is that enough for me to know what is the probability of infection? Two things here. Number one, you need to have that building already built and occupied and commissioned.
Yeah.
In CFD, I can do this even if your design is on the paper, and I can catch anything that is not right or going wrong at even conceptual stage of the design. That's the power of it. The second problem with the smoke visualization or any other tracer gas is it is as good as where you look at and where you measure it, where you put the sensors. How many sensors you are going to put in a breathing zone, for example, to get the complete understanding and picture of what is happening. As I showed you that cloud is 50% of the room is not good. It's their indoor quality is bad. I'm telling you visually, I can't draw that pictures by just measuring at 4 points in a room.
And you also can't leave the people in the room. But so my question being, how much do the people being in the room affect the fluid flows through the room?
Excellent question again. Thanks for asking that. People do two things. One is they are simply the obstruction to airflow. When the air comes to me, it bumps on me, it goes around me, and it changes the airflow pattern into the space. Correct? That's number one. Number two, which is very important and not obvious, is we all generate heat. We are the sources of sensible and latent heat to a certain extent. Hot air always goes up. As the air gets hot, it goes up. This is common sense, but it's not so common, even among the engineers, to know that hot air goes up. So if you have more and more people, it means you're putting more and more heat into the space. Now what happens is, if you supply the air at 55 degrees, by the time it comes to you, it is 65 or 70 degrees. And then when it comes to me or you, it picks up the heat. It gets hot and it goes up. So it can modify the airflow patterns into the space, depending on what type of people, what they are doing, whether they are running on in the gym or they're sitting and relax and watching movie, how much heat they generate depends on their metabolic activity. So definitely, presence of people can affect your airflow pattern and simulation itself and the performance of ventilation system.
All right, we're going to go to our halftime here, Dr. Khankari, and thank our sponsors. We'll be back, and in the second half, we're going to take another example and look at thermal comfort and how CFD is used to predict thermal comfort. We'll be right back.
Yeah.
Our marquee sponsor, Instascope. More jobs done faster with the future of IAQ assessment technology. Unlimited samples, instant results, and cloud-based data at instascope.co. Association sponsors are AIHA, Healthy Workplaces, A Healthier World, AIHA.org, ACGIH, Advancing Careers of Professionals in Environmental Health, Industrial Hygiene, and Safety, interested in defining their science, ACGIH.org. The Cleaning Industry Research Institute, see more deeply through science and research, CIRI science.org. The Indoor Air Quality Association, IAQA.org. The Restoration Industry Association, the granddaddy of the restoration industry, restorationindustry.org. The IICRC, a nonprofit standards development and certifying body for the cleaning and restoration industry, IICRC.org. Healthy Buildings America, Honolulu, Hawaii, January 18 through 20, 2022. HB 2021-America.org. Industry sponsors are AEML Laboratories. Free shipping, great pricing, same-day results with no rush fee, AEMLinc.com. Particles Plus, feature-rich particle counters and air quality instrumentation. Count on us, particlesplus.com. Gray Wolf Sensing Solutions, over 20 years manufacturing accurate, reliable IAQ instrumentation for portable, short-term, and continuous monitoring. GrayWolfSensing.com. TSI Inc., an industry leader in precision instrumentation for monitoring indoor air. Learn how to expand your IAQ investigations. TSI.com. Sunbelt Rentals, availability, reliability, and ease for all your IAQ and restoration needs at sunbeltrentals.com. April Air, healthy home, April, AIRE.com. And Healthy Indoors Magazine, a free online magazine for industry professionals and consumers, healthyindoors.com. All right, we're back. We're talking with Dr. Kishor Khankari about computational fluid dynamics and indoor environmental quality. Kishor, let's go ahead and go through that next one and talk a little bit about thermal comfort. And then I got a bunch of questions to get to, so we'll have to jump through this one pretty quick.
Yeah, just to clarify, there was a comment that smoke visualization has its own place and CFD has its own place. I totally agree with that. I totally agree. But I was just trying to compare the benefits of doing smoke versus pros and cons of these things. So I agree with that. Let's go back to thermal comfort here.
These are just tools in the toolbox, right?
Exactly. Can you see my screen now?
Yes.
Okay. Well, let's just a brief primer on thermal comfort here. First of all, what is thermal comfort? Most of the time, it's a psychological thing. It's a state of mind, correct? It's like happiness. You cannot measure happiness, correct? There is no absolute yardstick for happiness. Thermal comfort is somewhat like that. It's how people feel, it's their perception. But there is a science behind it also. It's how your body responds to the heat and moisture around you. So what scientists have done is they understood what you are doing, what is your metabolic rate, right? How much heat you are generating, what kind of clothing you're wearing, correct? Whether they are creating any insulating effect, what is air temperature around you? Most importantly, what is radiant temperature, whether you're sitting too close to the window or away from the window, humidity levels, and what is the airspeed around you. Remember why we start the ceiling fans or table fans? They are not the air coolers, they are air movers. The perception, when the air moves around you, you feel cool. That's what is the air movement. So what scientists have done is they collected all this data and they asked people, hey, how do you feel? Do you feel cold? Do you feel hot? Or are you just comfortable? And then they created these statistical models to correlate that data with perception of their comfort. And that is all captured in ASHRAE Standard 55 for thermal comfort of the occupants. All HVAC engineers should read, understand, and study ASHRAE Standard 55. I'm ASHRAE Distinguished Lecturer. I gave about 110 lectures worldwide so far. And I ask these questions in all my lectures. How many of you know there is a standard for thermal comfort of the occupants? Only 5% hands go up. And I ask those 5% people, how many of you really use it in your design? Not even 1% of that 5%. So buildings are for the people. We need to appreciate and understand that. And everything we should do to make people comfortable, healthy, productive, we should use all the tools in our toolbox to make sure we ensure that. So what happens is, now in CFD, when you do any CFD simulation, you know the air temperature, you know radiant temperature, you know air speed, and what you can input into CFD is, hey, what this person is doing. Is he just sitting and working at his desk, or is he jogging in the gym, or what the person is doing? We can input that and say what kind of clothes this person is wearing. Once you put all that, you can really create. Let me see. I can share this now. You can create a simulation where I actually know how people will feel in that space. I can estimate that. Correct. Percent mean vote is ASHRAE Standard 55 index. So it goes from -3 to 3. 3 means people will complain it's too hot. -3 means they will complain it's too cold. In this picture, the red color where the hot window is, when this guy walks to the window, he's going to feel too hot. Okay. And then if he walks towards the door away from that window, he will be about comfortable, not too cold, not too hot. Now, the reason for this, that's where CFD comes into picture. Why it is hot there? Why this person will feel hot there? Because it is close to the hot window. And in this design, they did not address that when there is a perimeter load, when there is a hot window, we need to inject the cold air in front of that window to take care of that. This design somehow is missing that point. When I did the other simulation and I added a passive chilled beam on the top of that window, passive chilled beam is just the cold coil on the top, it makes the air cold and cold air falls down, hot air goes up, and it creates kind of an air circulation, air curtain in front of that hot window. As soon as I put that in my model, you see that hot spot has gone.
Yeah.
Now, if you build this building, commissioned it, and let this guy go there and sit and work for 2 months, and then he starts complaining, are you going to put passive chill beam there? It's too late. It will cost you millions of dollars to make such retrofits into the building. I have a concern, Joe. My concern is our industry has enjoyed a passive consumer for over the years, over centuries. What I mean by passive consumer, we don't complain about our comfort, thermal comfort. We don't complain about indoor air quality. As I told you, if you sit in a restaurant and a draft comes on you, how many times you call a server or you call a restaurant owner and you say, hey, you know what? I'm feeling cold here in this spot. And all the customers who are coming, they will feel cold in this spot. You need to do something. What we think, oh, I'm just there for an hour or so. Right. I will ask server, hey, please change my seat. I'm cold here. And once we don't complain, the quality doesn't get improved. It's simple market law, business principle. If you don't like a cell phone, and if you return your cell phone, the cell phone company will change the model of it because you complain. We don't complain about indoor air quality. So we have laws for clean water. Do we have laws for clean air? Why clean air should not be fundamental human right?
Right. Right. Now let me ask you. You mentioned that you had all these inputs.
Yeah.
What information is needed to do the CFD simulation, and how do you get it? I mean, you mentioned radiant temperature. Well, somebody's going to have to measure that somehow, right?
No, it is predicted. It is
you predicted. Okay.
Yeah. So let me explain what is required. First of all, you need a geometry or information how your room looks like, how the space looks like. It has 4 walls. It has the ceiling at this height. It has this furniture element. This is how the people will be sitting here. And then we know where the air is coming into the space, where those diffusers are located, what type diffusers are those, how much air you are bringing in, what temperature you are bringing the air in, and then what other sensible heat loads you have, like whether you have what kind of lights you have, whether there are computers, what kind of computers, how many people, because people generate heat. Then you need to know how the air is going to get out of this space, correct? And then what kind of walls you have, where the glazing is, whether it's a double pane or triple pane, how much heat will come, outside heat, or how much heat we will lose from that. This is all input to the model. Once you put that, it opens up the door for wealth of information, your 3-dimensional airflow patterns, temperature distribution, thermal comfort, indoor air quality, concentration of the contaminants, you just name it.
Now,
but this, yeah.
I understand how this would be used prior to the building being built. Can you give us an example of how you use it after the building has already been built and we're getting an indoor environmental quality concern or complaint?
Honestly, it is too late, but
well, that's honest.
but it doesn't matter, because the engineer who did the job on that building has the drawing. So in other words, most of the time you don't have to go with your thermometer or your anemometer to go and, hey, Kishore, here is the wall temperature, or here is the supply temperature. We know, your air handler knows how much air you are supplying to the space and what temperature you are supplying to the space. And the beauty is, if you say, well, the occupancy is for 50 people, but we never get 50 here, we only 15 people get into the space. On the model in CFD simulation, we can change the occupancy from 15, 20, 25, 30, 40, 50, and see what happens to the space. So whether the building is on the paper or actual building, CFD procedure is the same.
And do you have to model every room, or can you when you're doing a building, especially, I guess, in the design phase, because this costs some money, do you have to do every room?
You don't have to do every room. That's the beauty of this. And this is an excellent question. Let me tell you why. CFD is a tool. Try to understand, it's not the end in itself. I always give this example. If you are hiking in dark woods in the nighttime, you don't have flashlight in your hand. You may fall off the cliff. You don't see your way. What flashlight does? It shows you the way. But flashlight is not a GPS system. It's not going to tell you take right turn, left turn, go straight. It shows you the way, and it helps you not to fall off the cliff. CFD is like that. It's a flashlight in your designer's hand. So you can use this as a tool to find out potential problems. And what can I do? What can I do more to make my people happy, to make my people comfortable, to make my people breathe the right quality air into the space? If I am compassionate about the people, then I will do all those due diligence to make sure my design is going to help the people, going to create healthy building. Not just on the paper, not in your slogan, not just in your mission statement, but it's actually implemented and efforts are made towards that. So you don't have to do each and every room. Learn from it. Learn from every simulation. That's why gaining insights from your simulation is important. You need to be a good engineer first before you start using CFD. You should be able to separate out what is good and what is bad, what this simulation is telling me, what the physics is telling me. When I build next hospital, when I build next office space, when I build next operating room, what should I do? What simulation told me? So you don't have to do each and every space. At the same time, you should be smart enough to understand what you learned from which space and how this space is different. If this operating room is very different than the one you model, you need to do CFD on that one and learn new lessons from that.
Interesting stuff here, Kishor. Let's go to the roundup, Cliff and John. The Roundup is brought to you by April Air, providing healthy humidity, ventilation, and air purity solutions for new and existing homes. April Air, healthy air, healthy home at aprilaire.com. All right, let's, Cliff, do you have any final questions or thoughts for Kishor?
Yeah, I just have a question, Kishor. Can you share a success story with us? Something that, how this helped solve a problem or made something better?
Great question.
Yes, you need to invite me for another radio talk show.
There you go.
Mark, we'll do that. We'll do that.
I have plenty of these, especially when people are in litigation. That when you go to a doctor when you have severe pain.
Right.
If I tell you exercise every day, eat good food, yeah, sure, I heard it several times.
Right.
If I tell people you should do CFD, you should do DD, yeah, I heard Kishor 100 times his presentation. But I do a design and my owner sues me, say, hey, you didn't do it right. So people come to me and then they beg, please show my design is right. I say, who am I? Who am I to show your design is right? The physics of the situation will tell you whether you did the right thing or not. And if you are so concerned, you should have done CFD before you put the things in place, correct? Now it is in the litigation, things are not working. CFD can only help you or show you a way to get out of litigation. Okay, so I did that. I have an article on patient room, and generally, when they design patient room, they don't care where they put the written in the patient room. I have showed that if you put the written on patient's face or the patient's head in the ceiling, that works better. All the germs will go up from there and will not spread into the room. And I showed it by simulation.
Understood.
This has been fascinating. It went way too fast as well. I just, before I knew it, it was time for the roundup. But anyway, can you give me a ballpark idea on what this costs? People always, what does it add to a project?
Yeah, I can give you ballpark very well. Before that, let me tell you, if the design costs $1, the construction will cost you $10. Operation of the building costs $100. And people who work in that building cost $1,000. The cost of people is 1,000 times the cost of design. And buildings are for the people. When people ask me how much it costs, I ask them, how much your people cost to you?
Right.
What is the price tag on human life? What is the price tag on my comfort? What is the price tag on my indoor air quality? What is the price tag on my health? To answer your question directly, 10% of your design cost. It means 10 cents will save you $1,000.
Interesting. And how reliable are these computations, Kishor?
It is a tool. It is a tool. And it is not, if you do a simulation, don't come back to me and say, Kishor, you predicted 78.3 degrees Fahrenheit and my building is showing 83.6 Fahrenheit. I asked them, where I showed you a hotspot in a building, is the hotspot there? Guaranteed hotspot is there. What we need to look from CFD simulation is the trend, is a tool to help me guide in right direction. No simulation is absolute. No simulation can replace the physical reality. That's not the purpose of simulation. Purpose of simulation is to learn, refine, and design better buildings. That's why we should use CFD.
Wow, that was a great answer. Now, who are your clients? I'm just curious. Who's ahead of the curve enough to be using you to help with the design of their buildings?
Yeah, on a broad brush, I can say I have two types of clients. One client who is visionary, who understands the value of people, their health, their comfort, and another client who is in deep pain. So these range from owners, facility managers, design engineers, design firms, architects, all these people. They are my clients. They and once they know that this pill helps me to remain healthy, they take that pill again and again. So I want to emphasize that you should look at it as a tool. It's like a thermometer, correct? A thermometer doesn't cure you. Thermometer just tells you whether you have fever or not.
And just before we go, is there anything you'd like to add? I know we went through this real quickly and there's a lot more detail, but anything we missed that you want to make sure you get through to our audience before we go?
Yeah, I'm passionate about health, comfort, well-being of the people. I'm passionate about how buildings should help to deliver all these things to the people. I want to tell everyone, buildings are for the people, and do everything you can do to improve indoor air quality, thermal comfort, well-being of the people, and do your due diligence. I'm not here to tell people do CFD. I'm here to tell everyone, be compassionate. Bring the compassion in your design. Before you build a school classroom, think if your son or daughter is going to go in that classroom, will you build that classroom the same way you're building it now? And if the answer is yes, then you are doing everything to ensure the children in the school are safe and they have the good learning environment.
I've got to add one more thing. When we talked earlier, you said, if you want to ensure good indoor air quality, educate the people. Give us a little more on what you mean by that.
I want to educate the common people. I want to tell them the same thing. If I give you a dirty glass of water, will you drink it? No. How do you know what you're breathing in? What you are breathing? The education of the engineers, education of facility managers, education of building owners, education of common people. All the people, you, me, and everyone else should know, don't take your indoor air quality for granted. Demand it. Ask from the building owners. Ask from the design engineers. Ensure me, show me that you have done everything to give me the better indoor air quality. That's what I mean by education.
I can't think of a better message to end this one on, Kishor. Thank you so much. Always a pleasure.
Thanks for the opportunity.
All right. This is Radio Joe Hughes saying thanks to our guest, Dr. Kishor Khankari. I also want to thank my co-host, the Z-Man, Cliff Zlotnick. John, you got to have faith at the controls. Most importantly, our growing group of loyal listeners and sponsors. We'll be back next Friday with the next episode of IAQ Radio Plus.
For IAQ Radio, I'm Spike Reel saying thanks for listening.